Everyone, today we start numerical methods in unit 7. Today in this unit we will look how we can perform the numerical differentiation. This unit is divided into three main components based on numerical differentiation, high accuracy differentiation formula, and Richardson extrapolation. So in calculus, we normally interested in mathematics of change because engineering, most of the application is based on rate of change. So we have to go for the dynamic analysis and things like that where we need to find the derivative. Now, standard in the heart of calculus as mathematical concepts of differentiation and integration. So in this unit we will only discuss the differentiation. For example, the idea is given here. If time and displacement is given, and if someone asks us to, based on this data set, calculate the speed, so it's not straightforward to do it. If we do it based on the only first and last data points, then we are not able to calculate good approximation for differentiation. So we have to come up with some algorithm that can help us to do that. Now, how do we evaluate the derivative of a tabular function? This is the thing that we will discuss in this unit. How do we determine the velocity acceleration from tabular data? Now, we will start with the finite divide difference approximation of the first derivative. So we actually discuss forward difference, backward difference, central difference. So based on this, we have to use the Taylor series. So if we consider a Taylor series based on x plus h, so we can approximate it using Taylor series as f of x and its derivatives accordingly in series. Similarly, we can calculate the function values during that Taylor series with x minus h. So we will use these formulas to come up with forward difference and backward difference formulation. So the idea is that if you have a true value here, in forward difference we are using the next point to approximate this derivative. So we are actually using f plus h to calculate the derivative. We call it as forward difference. So based on this, if we because we are interested in first order differentiation, we will avoid all the other terms and we call it a big O of h, means that higher order terms, because they are based on h square. So we wrote here h square. So when we solve this, we can come up with formula for feed forward difference. So just take the differentiation on the one side and we just divide with h and we come up with this formula. Because h is there, when we divide with h, so h squared become h. So this means that the error term is based on the h for forward difference formulation. Similarly, we can look for the backward difference. So backward difference, the only idea is that we use the previous point to approximate the derivative here. So we use the Taylor series f x minus h in that case. So when we do that, we come up with this again the same term with higher order h square. So we will reformulate it and we come up this formula. So again it is of first order of h. So this means that the error term is based on h. So as you increase or decrease h, it has a direct relation on the error of the resultant differentiation. Now we want to improve this error terms. So we will come up with another idea. We will use the central difference, so in which we will try to accommodate forward and backward difference. So how we do that? Actually we call it central difference. So we will using the previous point and the forward point to come up with the formulation. So it's very easy. If you have the forward difference and backward difference, if you take the difference between forward difference approximation and backward difference approximation, then you come up with this result. Now here we have h square as the error term. So this means that the central difference actually is much better than backward and forward difference formulation. Now here we come up with a summary of three methods. One is forward difference, where we have f of x plus h minus f of x divided by h with accuracy of big O of h. Similarly, backward difference using a backward point with same accuracy, but central has better accuracy than forward and backward differences. Now these are the formulas for forward and backward difference. Now it's very important to know that this big O of h, because we are not using the higher terms of the Taylor series, we call it truncation error order. Okay, it is indicative of how much the error changes when h changes. Now forward and backward different formula are comparable in accuracy. So central formula is expected to give better answer. The idea here is the simple that we are using more points to calculate the difference. Now let's see what actually happened in graphical. If this is a function and this is the derivative, so if you are having a point here and you are using the previous point, we call it backward difference. So if you are using the next point, we call it forward difference. And similarly, if you are using the both, we can call it as central difference. Now graphically we can represent this if we simulate this using MATLAB. So we consider sine of x here. So the point we are used for calculation of the derivative is represented as a red steric here. Now if you see, the green line is the forward difference, and similarly you see the red dotted line as the backward difference. So they are having this almost the same variation from the original line. Original line is the true line, is the solid purple line which is actually representing the true differentiation. But surprisingly, if you see that the central difference is much near the true differentiation. Now we see a numerical example to see how these methods work. So here in this numerical example, we will apply forward, backward and central difference. We are interested in derivative at point x equal to 0.5 with two h values. One is 0.5 and other is 0.005. Okay, 25. Now this is our function. So for comparison, we just want to know the exact value. Because this is an analytical function, we can easily find the exact differential. So we take the differential and we want to evaluate at 0.5 to get the true value. So value is 0.9125, all right, minus 0.9125. Now let's apply for h 0.5. For h 0.5 we have to find the next value. Because x is 0.5, so if we are using the forward difference, then we have to add 0.5 into it so that we get the forward point. Similarly, we have to subtract 0.5 from x so that we get the backward point. So this is formulation that we have to do, and we need to calculate the function value at these points. So we do same thing here. For look here, x is 0.5. When we subtract from 0.5, we come to 0, and this is x function value is 1.2 that we use for backward difference. Similarly, when we add a point, we come up with 0.2. So we need three values, and these are enough to calculate forward, backward and central difference. So we just plug these value in the formula and come up with the solution. So this is forward, next one is the backward, and then the third is the central. So when we do that, we come up with the first solution for forward, then backward. So look here, forward we have 58.9% is the percentage relative error. Similarly, backward is a bit better than the forward, is 39.7%. But central, look here, it is 9.6%, much better on both of them. So it is numerically verified that we have much better solution using central difference formula. So similarly we will reduce the h. Now when we reduce the h, we assume, so we get much better result. So look here, we improve our forward from 58 to 26.5. Similarly 39 to 21.7% is improvement in backward, and central is 2.4. It's amazing. So from here we understand from this numerical example that forward, backward and central difference, central difference is better in any way if you are using any type of h, if you are comparing with backward and forward. But surprisingly, as you reduce the h, you have much better accuracy. So for both step size, the central difference approximation is more accurate than forward or backward difference. Also, as predicted by the Taylor series analysis, halving the step size approximately halves the error of the backward and forward difference and quartile the error of the central difference. So this is what we have. Now I will stop here. We will continue further discussion in the next video. Thank you.